All right, so this video should be a little bit shorter. We're just going to finish up the key ideas. You remember one of the ways of recognizing in this format if it was strong or weak is by utilizing the arrow. And that's certainly not a tell-all. Even sometimes they'll do a strong acid with a double arrow because, as you can see here, this is approximately 100% dissociation. So there might be just a tiny little bit of HA and H2O left on this side that didn't, or a tiny bit of HA anyway, that didn't dissociate, in which case you'd have to put a tiny little arrow going to the left on this one. So there are ways for us to recognize, once we know what A is in the other part of the acid, whether or not it's strong. And good old-fashioned memorization is the way to do it. Commit these to memory so that you recognize them. As you can see, there are some commonalities that will make things a little bit easier. For instance, there are 3 halogens, the exception being fluorine, that is not considered a strong acid. Even though it's a pretty nasty acid, it doesn't dissociate completely, and that's because of its small size. This then will kind of get you on the right track. This is perchloric acid. This is the perchlorate anion, perchloric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, and this is nitric acid and sulfuric acid. I think knowing the names and the structures of both of those would be important. So rewind that a little bit, write those names down if you didn't get that this time through. But that's the acidic 6. Know those 6. That's very, they call them the big 6. I like the acidic 6. You just need to know those things. Notice they are all in aqueous solutions. You aren't going to find a jug of just plain sulfuric acid. It has water in it. That's part of the definition of what makes it an acid. Now, the strong bases, this is the basic 8. Now, you don't see 8 listed here, but it does say all group 1 cations. And certainly hydrogen's not in the mix there. That's not in group 1. Remember, hydrogen is in a family by itself. But if you just use your periodic table, go right down column number 1, these are going to combine with hydroxide. So I think you should actually write the formulas of these down on this page so you have a good reference. So it would be lithium hydroxide. That's just LiOH because group 1, of course, they have a +1 charge. Sodium hydroxide, NaOH. Potassium hydroxide, KOH. Rubidium hydroxide, RBOH. And cesium hydroxide, CSOH. And then the hydroxide of these 3, I always remember CBS helps me, just a major network helps me remember CBS. They're kind of always together, like in solubility rules and certainly in defining strong acids. So when you write the formulas for these, of course, CaOH in parentheses 2, because these are +2 ions. So SrOH in parentheses 2, BaOH in parentheses 2. And you'll note now on this page you have a list of the baseful 8 instead of the hateful 8, the baseful 8. Those are the strong bases. So you will recognize those, and of course they would be defined as the same way that they tend to dissociate completely. And with this, it has very much to do with their solubility, of breaking up and just forming those OH ions as they dissolve in water. All right? Now, when these things pair up, it's a strong acid would always have a very weak conjugate base, and a very weak acid will always have a very strong conjugate base. That's a back and forth kind of thing going on. Now, if you think about it, if something was like unwilling to, loan out your pen, you're like, okay, I'll let you use it. That person is going to want your pen back, okay? Whereas if somebody was like, I got 1,000 of these, whatever, here, take it, and getting that pen back is not such a big deal. So it's that give and take that creates this thing, and mid-range, of course, would equal mid-range. So if you have something like HCl, that's one of the acidic 6. So it is definitely going to be a strong acid. Now its base is very very weak. Okay, so this is a strong acid with a weak conjugate base. So does it want that hydrogen back? This already gave that up and did this, so it's not going to happen in reverse. But if you look down here, water, of course, is a very weak acid, and that water then will turn into OH, which of course we know is a very strong base. It's the definition of being a strong base if you're just a OH ion floating in solution. And I think this is a really good example too. You look at methane, which you know is a very stable molecule. If you were able to somehow rip off a hydrogen, this is going to be very, very unstable. So it is going to want to grab that hydrogen right back to become methane, because we know how stable this is. So this I think should make a lot of sense to you. And you see hydrofluoric and ammonia in the middle. Those are your common acids that are not strong, not weak, that you will see used very often. All right. Now, one of the ways of looking at this is to think of there always being two bases in these reactions. We had talked about that. There's a base and a conjugate base. So if you look at this reaction, in competing for protons, okay, so the proton is going to go one place or the other. As it turns out, this being a acid is going to be a very weak base if you're competing for a proton. So it's like, man, this is the guy. I got tons of these. Go ahead, yeah, take that proton. And then the water will take that, and then therefore the reaction goes into completion. So it very much favors the right side of the reaction, because this exchange occurs because H2O is a stronger base. If you think of everything as in terms of their desire for wanting to take in a hydrogen, well, HBr doesn't want to do that. It wants to give it. So, whereas if you look at this reaction, ammonia reacting with water, you've got these products over here. Well, this is a super strong acid, right? So that hydrogen's going to end up there, and that is going to be the favored reaction, driving this whole thing to the left. Okay? So it's sort of a give and take thing. You see what's going on here with the products, and that's why it's a weak acid. Okay, and that's what that pairing means. Okay, so that is your introduction to acids and bases. Very important intro. You can start the homework now. See ya.